Can I get off screen though too?
All right, so good afternoon, everyone. We're Team 4, and this is a search and rescue robotic team by Randy Gonzalez, and this is Rover. So the motivation for our team is basically a search and rescue operation for stranded victims. And this project should pinpoint the exact location, which is usually a big issue when you're looking for victims, and it should also reduce the search time and number of personnel by utilizing robotic systems.
So yeah, what we have here is two robots working together. We have an airplane and a rover. The airplane is supposed to be the deployment for the rover. It's supposed to take it out ahead of the search team, and the rover will be scanning with a camera that's mounted on the rover. And once we have a target spotted, the rover is released from the plane, and from there, chutes open, it goes to the ground, it gets released from the chutes, and it can drive to whatever the target was and inspect it. So here we have the airplane that we chose for deploying the rover. It's radio controlled by line of sight, so it's not fully extended range. We implemented a release mechanism for the rover. Other features for the aircraft are it's lightweight, portable, modular, and it's easy to assemble.
All right, so this is the rover, and that's its final design, as you can see over here too. It has a radio control, it's going to be extended range. It has a first-person view camera, a shock absorber in the front so for the landing, so the arm doesn't mess up the motor itself, and it uses a treading system so that it's better for terrains. It weighs a little bit over 1 pound, and the airplane is actually able to carry it. And it also features, as you can see over there, that's a skyhook, so it can connect to the plane. This is the bill of materials for both the components. Some of these components actually have changed. We're not using the mini buggy no longer. We're actually using the Robot mechanism, and nothing else will be it, because the rover was too small to implement anything else on it. This is the modeling of it beforehand in SolidWorks. And this is a representation of what the release pin, as you can see over here, should do to the parachute mechanism once it lands. It's supposed to release it and also deploy the camera so you can view where you're going. All right, so we did some intensive testing of each individual components, and also they're integrated when you marry component with component. So we'll take you first through the individual ones, the testing that we made. Well, this is a quick release pin test. It's dropping.
So that pin would be holding the robot to the platform that the parachutes are mounted to.
Yes.
And once you raise the arm up, it releases it from the platform and the chutes.
All right, this is the first parachute test. And the parachute is actually 50-inch in diameter for the 1 pound block. This was done with a 1 pound block, but this first test was kind of unsuccessful because it was actually thrown up, and then, as you can see, it's very unstable in flight.
It sways around a lot with a single parachute.
Yes, and it actually landed upside down. So, okay. So, this is actually a 2 parachute test, but actually dropped from a high altitude, basically the parking lot from the main campus.
6 stories up.
6 stories up, rather than actually being thrown up by hand. As you can see, with 2 parachutes of 50-inch diameter, it's a lot stable fall, and it actually lands right side up with the parachutes on each side, so it wouldn't get tangled up once it lands.
Yeah, that was an important thing that we were looking into the rover. We want to make sure that once it lands, the chutes wouldn't come on top of it and render it useless.
Right, and this is a second test from lower altitude, and in this one we also store the strings inside the parachute, just the way it would be. This time it actually lands on grass, so you can barely hear it once it lands. It still landed right side up, as you can, I did the inspection right there, and those are the bolts, which suggest it landed right side up.
Okay, so this flight here was done without a payload. This is the airplane that we chose to use for deploying the robot. no weight was on it. We just were trying to get a baseline for how the aircraft performed, and then you could see the difference as to what happens once you add, basically you double the weight of the aircraft with this robot.
You see those two paper cones, those are the parachute storage system, and it's also included, it's very lightweight, the load bearing bay and also the release, the deployment mechanism for the rover.
Yeah, so in attaching the robot to the plane, we needed two systems. First, we needed something that could handle the weight of the robot in attaching it to the aircraft, and we needed something that could release that weight. So we built a structure in there, a box type structure that holds the robot, and then there's a pin that releases it.
From this, this attaches to the box, and this actually holds the pin. Once the pin turns, he'll show you in another test that we
Yeah, there's another test that goes through that. So as you can see, yeah, without the weight, the plane flies really slow. It's much more forgiving, more maneuverable. You can see it's much easier to fly, and landing as well. Well, landing is a lot slower. So,
You're good?
yeah.
All right, for this, after the individual components testing phase, we also went to the integrated system testing. As you can see here, this is what the entire system would look like on the plane. Of course, it's missing the wing at that moment, but we'll take you through each one of them. You want to show them something?
Oh yeah, so this was the box that I was talking about. It's the load bearing that connects the weight of the robot to the plane, and then over here we have a servo that's linked to a pin that releases the robot once it's in the air.
All right, this was the Rover remote control test. We basically
Spit it out.
yes, we basically took it to the robotics lab, hooked it up to a TV, and started driving across the hallway just to see what's the extended range of the camera and also the
radio transmitter.
The radio transmitter. We found
we also did recognition testing. So like I left an object out there, and he had to drive up, find it, and tell me what it was. And there was the little safety pin.
Also, it should be noted that the walls actually prevented from reduce the range of the camera and the radio control for the rover as well.
And it's very slow on the trains.
Very slow. This is 8 times faster.
8 times faster, so you can see that it's pretty slow.
Yes. You can take it all the way. When I take it to the corner, and then you walk it back. Yeah, I actually made it past the corner without losing control. Of course, when you're outside, it's a lot better. All right. Well, so this is a parachute platform release test, just as you saw in the modeling. It's supposed to release the platform from the parachute system and drive off. As you can see right there, the pin.
So there's a rubber band that's connecting the robot to the platform right now, and we went with a rubber band because it doesn't really require that it bears much load. All it's carrying is the weight of the platform, which was foam. So that platform there.
We have it right here with the parachute. Okay, so that was that test. And this is the actual rover being thrown off a building with 2 parachutes. So fingers crossed. It's actually very slow, but as you can see, it flipped due to a high center of gravity. Definitely recommend a different platform. Maybe raised above it or with what was it you said, Robert?
Well, we would want spacers between. Like the way we had it, the strings to the parachutes were down low compared to the robot. What we want to do is actually mount them up higher so that there wouldn't be a tendency for the robot to roll.
To flip. All right. After that, the robot was still working, thankfully. And this is a rough terrain navigation, which...
we also wanted to make sure that it released from the platform.
Yes. However, it didn't perform very well on this test.
Yeah.
The treads are actually very...
the treads on the robot are very loose. So you can see, you could easily lift them up and off.
Yes.
That means if there's any sort of obstacle that it gets hung up on, it's just gonna, the servo's just gonna spin through and not even move the tread, which is what you see happening here. if we had a tighter tread system, then this grass wouldn't be so much of a problem. So now what we have here is the robot attached to the airplane. Another thing that we had to consider was the weight, the additional weight on the airplane. We didn't want it to flex the wheels out too much so that the robot was actually dragging on the ground. So we reworked the landing gear on the airplane to make sure that it could still roll, take off, and land, and do it all safely.
No, this test was definitely a success, except for that bump.
Yeah, that was a bump.
So, okay, and this is the deployment test for the rover from the airplane.
Yeah.
This is just to make sure that it actually works and can I release it.
So this is the load-bearing mechanism, and this is the release mechanism. And as you see, it'll fall out.
But you have to play with the servo a little bit, but it's still successful nonetheless. So this is all system flight test number 1. However, we did it to preserve the equipment. We actually did it with a dummy load instead, so that if anything, if we lost anything, we only lost one robot.
With this dummy, with the dummy load, it's actually a little bit heavier than the robot, but I was anticipating using a